Okay. Oh. So last time we got started with chapter 7, finished up chapter 6. This is usually about the time the students start looking at me like, how are we ever going to make it through this class? Well, the good news is we're almost halfway done. And right about here is where the class starts to kind of, it's not really going to get any more difficult at this point. It's only going to kind of stay about the same for a little while and then get a little bit easier. By the end of the semester, things are really a lot easier than they have been so far. So the good news is that the increasing difficulty is not going to happen anymore. It will still be. We'll still have some tough work, but nothing any more than we've done so far. The other good news is that I was just looking at everyone's grades, and I'm pleased with how well we're doing here. This is actually a pretty good class as far as my experience is going. We're all at a level that is quite good in the homework, and exams are looking good, and nothing. I don't see any glaring things to worry about. Your grades on my open math will not look complete because I haven't entered any lab grades in or quiz grades in. I have to enter those by hand, and I'm notorious for putting those off to the last second. So essentially what you need to do to figure out what you're getting in the class is look at your overall homework grade and your overall test grade and just kind of take an average, and that will give you a rough, kind of a rough idea of where your grade is in the class at the moment. And you should also look at, on my open math, I think you can choose as a student to look at your average for past due assignments only, and that's the one you should look at. If you look at the average for all the assignments, of course, you haven't done all the assignments, so your average will be much lower. Just look at the average for the past due assignments, past due exams, or whatever, and then just take a rough average between those two, and you'll be in good shape for understanding kind of where you're at. Excuse me. So, quick review from what we did last time. We talked about different kinds of energy. We talked about work energy. Work energy is the kind of energy that is occurring when a force makes something move. So if a force moves something some distance, one point to another point, then that is work being done. It has to be in the direction that the force is acting. So if the force is pushing to the west and the object is moving to the northwest, then that counts because northwest is partially to the west. If it's pushing to the north and the object is moving to the west, it doesn't count. That's not work, right? Because the force is acting in one direction, but the movement is in another direction. This was the case with the person pushing the lawnmower, where they're pushing downward on the lawnmower, but the lawnmower is moving forward, so it's kind of a downward forward movement, but the forward movement of the lawnmower is partially in that same direction, so that counts. In other words, part of the force is in the same direction as the movement. But with the person holding the briefcase and walking sideways, the movement is sideways while the force to hold the briefcase up is upward. Those two are 90 degrees from each other, so they're not in any of the same directions with each other, and there was no work being done to hold the briefcase up at that point. We also talked about the idea of the idea of this cosine of the angle theta between the force and the distance, where if we lift something straight up, or if we take it upstairs at an angle, this cosine of the angle between the force and the distance will actually make these two situations have the same amount of work for the same briefcase. If you go up the stairs at the slanted distance, or if you go up or down, straight up or down using an electric generator, same idea, same amount of work because of that cosine theta here. Here you have essentially a smaller force but a bigger distance because of the cosine theta. And here you have a bigger force and a smaller distance. When you multiply them together, they give you the same number. And of course, calculating the work comes from work equals force times distance times cosine of the angle between the force and the displacement. So work is a kind of energy. And what work does is it changes force. The idea of work is that force can create a change in kinetic energy, or a change in movement, a change in velocity. Work transfers energy from one kind of energy, force energy, into another kind of energy, which is movement energy. And what is this movement energy? We went through all this hullabaloo and this mathematics and everything else, and we discovered this 1/2 mv squared thing, which we called kinetic energy. An object that is moving, no matter how it's moving, has energy that is associated with that movement is actually a type of energy. Mass that is moving carries a type of energy with it. We call it kinetic energy, and it's calculated by taking 1/2 times the mass times the velocity of the object squared. Because this has mass and velocity squared in it, it will always be positive. Kinetic energy cannot be negative. Even if you're going backwards in the x direction, that negative velocity will still be squared and become a positive number. So kinetic energy is one of the few things in physics that can only be positive. Mass, of course, is another one of those. So mass times velocity squared will always give you that always positive kinetic energy. The net work that you do on an object, which of course involves the net force that you do on an object, that you apply to an object and the distance that it moves, will equal 1/2 mv final squared minus 1/2 mv initial squared, or the difference in the kinetic energies. So, what this means is that if you push a car and it changes velocity, then you can plug in the change in velocity here, put your final one here, your initial one here, plug in the mass of the car here and here, plug in the 1/2, take the difference between those two kinetics, and you can actually calculate how much work was done. Or vice versa. If you know how much work was done and you know the final velocity or the initial velocity, you can calculate the other velocity. So you can rearrange this equation in many, many different ways to calculate for unknowns. Initial velocity, final velocity, even mass, or the net work done. But remember that net work is force net times distance times the cosine of the angle between them. So if you plug in force times distance times cosine of theta in place of this work, then you can also solve for the force or the distance, right? Or the angle between the force and the distance. You can solve for any variable in there if you have everything else. And this becomes a much faster method for calculating things in movement than kinematics. In kinematics, you often had to use 2 equations or 3 equations to get your answer, and there were vectors involved and everything else. In this one equation pretty much does it. Here is an example where they solved this work energy equation, work equals 1/2 mv final squared minus 1/2 mv initial squared. They solved this for the 1/2 mv squared final. In other words, they're trying to find out their final velocity, and when they solve it in the end, they get this equation that has a square root in it. And that's if your initial velocity is 0. If your initial velocity has some value to it, then they actually don't show it here, but you will have another term underneath the square root. It's in another example that we're coming up on. Here they use the same thing to solve for, they're actually, in this one, they're actually using work done by friction equals force of friction times distance of the friction. They're using just the work equation to solve for the distance that something will slide as friction is slowing it down. So lots of different things that you can do with these equations as you mix them up, scramble them around, or whatever else. So you have the work done by a force. Work equals force times distance or displacement times the cosine of the angle between the force and the distance, right? Then you have the work energy theorem, the work, net work, so all the forces added together times distance times cosine theta would be the net work. That net work is equal to the difference in the kinetic energies of the object that's being moved. That's the work energy equation. And then they also rearranged that first equation, work equals force times distance times cosine theta, with friction, where work done by friction is going to be equal to the force of friction times distance times the angle between. And then they introduced the idea of potential energy, where if you lift something up in a gravitational field, if you lift something up higher, it has this potential to fall and gain some kinetic energy, right? It has a potential to fall and hit something and break it, use its energy to break things or to make sound or heat something up or something like this. In this case, they lift up this acorn mass, this acorn weight, and inside of here it turns a bunch of wheels and gears and springs and stuff. And then as it falls down, it turns those gears and springs in the opposite direction, and it keeps the clock running. This is what keeps clocks running. It's always some kind of mass or some kind of drive that is pulling on these gears and making things move back and forth and around and around. I mean, you could use batteries to do it too nowadays, but all the great classic clocks and watches use some kind of potential energy that you store by lifting a mass to a higher place and letting it fall downward. And this potential energy equal to m times g times h. Mass times gravity times the height, or the difference in y, difference in the y direction. M times g times h. And these energies can be traded back and forth. You can turn your potential energy into kinetic energy just by letting something go and letting it speed up. The potential energy will turn into gravitational energy. Into kinetic energy. And kinetic energy, as something is moving along a track, can be turned into potential energy if the track bends and goes uphill. And that kinetic energy then, as the car slows down going up the hill, is being turned into potential energy as it goes higher and higher and higher. So these things can be traded back and forth. The most important thing about potential energy is you have to choose a 0 point. If the ground here in this picture is your 0 point, where you're going to say this is 0 height, then everything above that would usually be positive height, and everything below that would be negative height, which means that potential energy can be negative. If you're below the 0 point, you can have a negative potential energy. And that just means that it has a negative in front of the number when you put it into the equation. The math knows how to deal with it from there. In this case, they have a person who's jumping onto a floor, and his knees are going to compress as they stop his fall from 3 meters, right? And they compress just a little bit, like a half a something, half a centimeter, say 5 millimeters or something like this. Half a centimeter, so 5 millimeters. We want to know how much force that is on the joints. Well, remember that the knee joints at this point are doing work to slow down the jumping person, right? They're pushing on this person, and they're slowing this person down. So that work is going to be equal to force times the distance times the cosine of theta, since they're falling down and the knee joints will be pushing up. The angle is 180, the cosine of 180 is 1. It's actually -1. So that's why it becomes negative force times distance. The force is the thing that we want to know. We know the distance is 5 millimeters. But we want to know what the force is. Where does the work come from? How much work has to be done? Well, the work that has to be done has to be equal to the amount of kinetic energy that the person has right before they hit, because that's how much energy they have to remove from the person's system. That's how much energy has to be removed to slow them down. But how much kinetic energy was there? Well, the kinetic energy came from the potential energy when they stepped up to the top of the room or whatever. When they went up higher in the room to jump down to lower in the room, right? And so this height change has an energy associated with the potential energy, mgh. And this is why at this point they say that the kinetic energy at the bottom of the jump is equal to the negative of the change of potential energy, which is negative mgh, and that the work that has to be done, which is going to be equal to the negative of the kinetic energy, is going to then equal the mgh, because mgh is equal to the negative of the kinetic energy, right here, or negative mgh equals the kinetic energy. So in the end, you get the work done by your knees is equal to the amount of potential energy that was put into the person as they climbed up to the top, to the 3 meter where they jumped off from. In other words, it took the same amount of energy to walk all the way up the stairs as it does to stop the person when they jump from the top of the stairs to the bottom. Same amount of energy. You put the energy in by walking up the stairs. You take the energy out by jumping, turning it into kinetic energy, and then stopping at the bottom and removing all that kinetic energy in your knees, right? By applying a force with your knees. So if work is equal to mgh, then they just did they used the work equation, force times distance, and there's a negative there because of the cosine 180 degrees again. And then mgh, of course, is they're just numbers, and they're solving for the force, they know, so it ends up being negative mgh over d. They plug in all the numbers and they get this value for the amount of force on the knees. Now that's a lot of force. 300,000 newtons is significant, painful even. Break your legs. So if this is true, if these energies can switch back and forth from one to the other, then we can do a problem like the roller coaster problem. We start off with potential energy equals mgh at the top, and all of it turns into kinetic energy when we get to 0 point. This is the 0 point right here. All of that potential energy has to equal the kinetic energy. So mgh is going to equal kinetic energy, or change of potential energy equals change of kinetic energy. And this brings to light a new equation, which we call a new idea, which we call the conservation of energy, where energy is just moved around in the universe, but it's never like destroyed or created in the universe. As I mentioned before, that's not exactly true, but you have to get to the second semester to understand more about that. And we need Uncle Albert. But if you have forces that are not going to turn your energy into some kind of a heat or some kind of a sound or break something, the kind of forces that make things into heat or break things or cause sound, those are what we call non-conservative forces, right? It's like Humpty Dumpty. Can't put the egg back together again, right? It's non-conservative. Once the egg's broken, time to make an omelet, right? Same thing with sound. Once the sound is made, it's very difficult to capture that sound and turn it back into energy that I can use to make more sound with or something else. Sound is something very difficult to recapture. Once you've said something, kind of wanders out there into the universe and just becomes energy that's just random out there somewhere, right? It's not like, texting or something, you can save it forever. You can record sound, but that's not exactly saving the energy. It's just using the energy of the sound to do something else. And so anyway, if you have a conservative force, well, what are conservative forces? A lifting force and a pushing force are fairly conservative forces. They don't create a lot of heat between the objects. They don't create a lot of energy that dissipates and kind of wanders away. So lifting forces, pushing forces, those are fairly conservative forces. It's they're not bad things for that. And one of the things that does pushing and pulling a lot is our springs. These are one object that's in the world that does a lot of pushing and pulling. And so what happens if you push or pull a spring? Well, if you push or pull a spring, it actually stores energy in it as well. If you push a spring and compact it, it wants to push back out. It wants to extend back out. If you pull it and stretch it out, it wants to pull back in. It always wants to be at that equilibrium point for the spring. So what is that energy that is stored in the spring? How do we talk about that potential energy? Because it is potential energy. Well, we know that the force that a spring exerts is directly proportional to the distance that you stretch it or compress it. And that ends up giving us a force distance diagram that looks like this. And as we said before, the amount of energy or work done is equivalent to the area under a force distance diagram. And this is a triangle. So a triangle, the area under a triangle is 1/2 times the base. The base is x, times the height. And the height in this case is k times x because of what's his name's law? Hooke's law. And so 1/2 k times x is 1/2 kx squared. And that's where this equation comes from. So we have the potential energy can be stored in a spring. So if you have something, a ball that hits a spring and compresses it, and you freeze it right there while it's compressing the spring, then some of the kinetic energy from the ball turned into potential energy as it compressed the spring. And when it's done compressing the spring will try to expand outward again, and will turn that potential energy in the spring back into kinetic energy in the ball as the ball gets bounced off the spring. I did lots of experiments like this on my trampoline when I was a kid. We had a trampoline back in the 70s, which was way before trampolines became readily available to the general public. My parents bought an Olympic trampoline, so it had a lot of bounce. Like you could get 20, 30 feet high on it if you were really good. And we used to put our cats on it. It was super fun. Cats hate trampolines. And they don't land on their feet when you put them on a trampoline, which is kind of funny. But their claws are dangerous on trampolines. So anyway, we used to bounce them and test these experiments and do, the potential energy as they hit the trampoline and the kinetic energy as they went bouncing off of it. Lots of things that are springy out there that you can store energy in. You have springs, of course. You also have cables and wires. And, I mean, just about anything has some kind of springiness to it. Even atoms, in fact. Atoms are the perfect example of things that have conserved energy in them. Atoms are, the nucleus of an atom is held together really in a really tight, small ball. The atom, your average atom is about 1/2 of a 1/10 of a nanometer. So you've heard the word nanometer before. A nanometer is 1/1000th of a meter. And then if you take that and divide by 20, then you get about the size of an atom, about 1/2 of a 1/10 of a nanometer. But the size of the nucleus is 1,000 times smaller than that. So the nucleus of the atom, where all the mass of the atom is, and all the matter of the atom is, pretty much all of it, is 1,000 times smaller. It's really tiny. But all the stuff that's in there, in the nucleus, well, most of the stuff, I guess we could say about half the stuff in the nucleus has this really, really strong, springy repulsion with each other, with the protons. The protons are positively charged particles that don't like to be close to each other, but in the nucleus, they're extremely close to each other. And the reason that they can be very close to each other is these other particles called neutrons. And the neutrons kind of have this attractive force in them. So there's this repelling, springy force, and then it's really strong, but there's this even stronger, attractive kind of sticky force holding them together. Right? So springs trying to push against each other in there, and kind of glue hold them together. So springy forces are everywhere, and spring forces tend to be fairly well conserved in very specific situations. So this is a good thing. So conservation of mechanical energy, what does it mean? Essentially what it means is that in certain systems, you can set up a system very carefully so that energy doesn't get lost from the system. It just goes back and forth from potential energy, gravitational potential, to kinetic energy, to spring energy, other kinds of energy. It just kind of goes back and forth, gets traded around the system so that the amount of energy you had to start with is equal to the amount of energy that you end with. It may be in different places, doing different things, but it's still the same amount of energy. And one way to describe this is to take this equation that we've already used, the net work equation equals the change in kinetic energy equation, and say that the net work is equal to the conservative, the network is going to be equal to conservative work, so conservative work will be equal to the change in kinetic energy. But conservative work is also often associated with lifting things in gravity, so that gravity can accelerate them as they get dropped in. So, and this one ends up being a negative PE because the gravitational force is down and it's in a negative direction. So you end up with a negative potential energy on this side and a kinetic energy on this side. So if you add the potential energy to both sides, you get this equation here. And what this means is, in the end, is that the kinetic energy plus the potential energy is always constant in a system where there's only conservative forces, where nothing escapes the system. No energy escapes the system by heat or sound or breaking things or things like this. So this is what we call conservation of mechanical energy. Often it's written like this, where you have the initial kinetic energy plus the initial potential energy equals the final kinetic energy plus the potential final. But it can also be written as kinetic energy plus potential energy at any time. Just at any time, measure them, it will always be the same number for a particular system. Then we did this example where the spring potential energy pushes the car and makes the car have kinetic energy, and then the kinetic energy turns into potential energy again as it goes up the hill. Or it turns into more kinetic energy as it goes down the hill. And then that more kinetic energy turns into more potential energy as it comes back up the hill. Either way. So in the case of when you have springs involved, that spring thing is included in the potential energy part. So we have a kinetic energy initial, we have a kinetic energy final, then we have two potential energies. We have a gravitational potential energy and a spring potential energy. Gravitational final, spring final potential energy. So the kinetic energy there's only one of right now. The potential energy we've got two of right now. And all the stuff added together at one point has to equal all this stuff added together at any other point. And then in particular situations, you might have zero potential energy. So that part goes to zero, or you might have zero velocity. So that part goes to zero. It's always a good idea to know what's happening in the problem so you can cancel out some of these terms, make this equation simpler. That's what they did here. They had two terms that cancel out, the kinetic energy and the potential energy canceled out. Here in the first on the left half, and then at the end of the problem, everything cancels out except kinetic energy. It all becomes kinetic in the end. And then you can solve it and be done. So now this is where we kind of ended up, which is the non-conservative forces. And essentially what it comes down to is friction. Um, One other difference between conservative forces and non-conservative forces, when we talked about lifting things up in gravity, we said it doesn't make a difference if you walk it up the stairs at an angle or if you lift it straight up. And that's because conservative forces don't care what path they take. They're not losing energy based on the path they take. They're not gaining energy based on the path they take. It just depends on where they end up in height or where the spring ends up being compressed or something like this. All that matters is the beginning and the end. But with non-conservative forces like friction, it really depends on what the path is, because the longer the path, the more energy is removed by friction. Friction is something that depends on, those two things rubbing together. If they're rubbing together for a longer amount of time, there's going to be more energy lost. So friction is a very path-dependent thing. If you take this path through the smiley face with friction between you and the smiley face, you're going to have much less friction than this path, because this one here has 2 or 3 times as much path length. So, if this system has no friction in it, we have a perfect spring down here that doesn't heat up, there's no friction at all, you'll have all potential energy at the top before you drop it, and then when you drop it, it'll turn into kinetic energy. The kinetic energy will turn into spring potential energy. Then the spring potential energy will turn the energy back into kinetic energy. And then somewhere in between here in the top, you'll have kinetic energy plus potential energy. It'll be a little bit of each because we haven't gotten to the top. And then when you get back to the top, it'll be all potential energy again. If it's a perfect system, no friction, no heat loss, no sound, then this rock will go up to the same height every time. But in real life, that doesn't happen. In real life, the spring absorbs a little bit of energy and heat the heat dissipates away. It makes a little bit of sound, and that sound goes away from the system. You can't capture that and reuse it. You have friction in the air that dissipates as heat or whatever. So there are lots of things that make this an imperfect system, so that every time it bounces, it comes up a little bit short of where it was to begin with, and then a little bit less and less and less and less and less. If you have a completely non-conservative system, you just drop the rock on the ground. It starts off with all potential energy. Right before it hits the ground, it's got all kinetic energy. And then all that kinetic energy turns into things like sound, the ground, making a dent in the ground, maybe breaking the rock, heating up between the ground and the rock, heating up of the air, heating up the rock in the air. All these different things that happen to leach out energy from the system. And the bounce off the ground won't be nearly as much as the bounce off the spring, because it's lost so much more energy as it goes through all these processes that are non-conservative. And how does that fit into our equation? Remember, we had our net work, and we had our conservative work. Well, now we're going to have non-conservative work, and it goes on the same side of the equation as the conservative work. Remember, conservative work was related to things like the spring and gravity, right? Whereas the net work was related more to the kinetic energy. So this ends up being this equation here, if we replace net work with the change in kinetic energy. And then we have our conservative forces in here, our potential energies in here. This non-conservative work is essentially going to turn out to be it's going to turn out to be just the work done by friction, or the work done by sound, or the work done by braking, or the work done by whatever. One of these things that is non-conservative, where the energy can just kind of leak away, wander away, and not come back very easily. So we have another baseball player problem, where the baseball player is going to slide to a stop on level ground with the friction. The friction is going to stop the person. Initial speed is 6 meters per second, and the force of friction is a constant 450 newtons. You want to calculate the distance that the 65-kilogram baseball player slides. So in our equation, we go back to this equation. This is our equation right here. We have our kinetic energy initial plus potential energy initial plus the non-conservative work. That's where your friction work is going to go, equals kinetic energy final plus potential energy final. And in this equation, he's moving when he starts sliding at his top speed. So he has some initial potential or initial kinetic energy. So we have a number for this one. This one we can't get rid of. But because he's at the same height at the beginning and at the end, there's no change in potential energy. Potential energy to begin with is the same as the potential energy final. You can subtract off both sides, and you're good. There's no spring. There's no spring forces, so we're good there. The kinetic energy final is equal to, if he slides to a stop, it's equal to 0. So this one can go away. So we've gotten rid of this one, this one, this one. We got rid of these three things. And we want to know the distance he slides. Well, the distance he slides is inside the work done by friction, because that's equal to the force of friction times the distance that friction is felt, which is how far he slides. So we replace this work NC with force of friction times distance, and we get this equation. Force of friction times distance, we get this equation rather. 1/2 mv initial squared, and it's minus friction times frictional force times distance, because the friction and the force are in opposite. The frictional force and the sliding are in opposite directions, so the angle between them is 180. Cosine of 180 is -1. So you get a negative friction times distance there, and then that gives you this equation. Then you divide by the friction. We know the mass, we know the velocity. Divide by the friction, and you get mv squared over 2f, which happens to be 2.6 meters. If you do it on a hill, then you might immediately think, oh crap, now I'm going to have to split this into forces that are going this way and everything else. No, you're not. You're not going to have to use dynamics or forces or anything at all. You'll need to know the frictional force, and you'll need to know the angles between things. It's no longer going to be 180. But right here, instead of our, excuse me. So here what we need to do is we need to know how high he goes. So he goes from this height to this height. So we need to know this is equal to h equals distance times sine 50 or sine 5, because it's 5-degree angle. So that's this distance that he travels times the sine of angle 5. So that's needed, because in the potential energy for friction, we do need to know. In the potential energy final, not the potential energy for friction, we do need to know the height. So mgh is mg times d sine theta for that little height of whatever it is. And then in the friction, we have the force times the distance, but in this case, the force times the distance is the same, right? The force times the distance is still a distance of d. It's still the negative frictional force, because the frictional force always acts opposite the movement. And then we have our initial velocity, our initial kinetic energy from our initial velocity here. And you solve this, and the math knows how to do it. It's good to go. Solve this for d, and you get 2.31 meters. You slide less distance going uphill than you do on a flat surface, which you would expect. And here's another one where they raise the ball up and then let it roll down. So the higher you raise it, the more potential energy you give it, which means that you can have more kinetic energy at the bottom. Let it roll down and see how long it takes. Determine the amount of friction from the stopping distance, I guess. So if you put a foam cup at the bottom and roll this ball into a foam cup, the ball is going to hit the end of the cup, and the cup is going to slide with some friction along the table. And however long it slides will be your distance, and then you can calculate the amount of friction by plugging the distance into this equation. For the force, for the frictional force, you plug in the amount of distance that you go. You don't know the frictional force, and you solve this equation for F instead of solving it for D or whatever else you're going to solve. So this brings us down to what we call the law of conservation of So we have our kinetic energy initial plus our potential energy initial. And the potential energies, remember, you can have different kinds of potential energy. You have, and in fact, you can even have different kinds of kinetic energy we'll learn about later. But you can have different types in each of these categories. You can have kinetic energies, you can have potential energies to start off with, and then your non-conservative works. So non-conservative work, which would be friction, which would be sound, braking, whatever else. And then we have other energies. So maybe there's electrical energy put in the system. Maybe there's some heat energy put in the system. Maybe, I mean, all kinds of other energies can be put in and out of the system. And then that equals your final kinetic energy plus your final potential energy plus your final other energies. The work goes on the side with all the initial stuff. And then the final stuff goes on its own on the right side. You can have chemical energy, nuclear energy, thermal energy, all kinds of energy. So they give some steps on how to do these problems here. Of course, you're going to determine the system of interest. This is important for energy problems. What is the thing I'm interested in? That's going to be my system. So if it's a bike rolling down the street, you're interested in the energy of the bike, or the distance of the bike, or the whatever of the bike, then the bike is your system of interest. And that's important because you want to make sure that you're tracking the energy going in and out of the bike system. Not energy going in and out of the street, or energy going in and out of the person riding the bike. Maybe the person riding the bike is part of the system, maybe he's not. If you're worried about how much energy the person is putting into the bike, then maybe the person is not part of the bike system. The person is his own system. So that's important to do correctly. Examine all the forces involved to determine whether you know or are given the potential energy from the work done by the forces. So if you already know how much energy is coming from a particular force, then that's great. If you don't, then you need to think about that. And then step 3, if you know the potential energies, the forces are all conservative. So if your forces are all conservative, you can apply conservation of mechanical energy without non-conservative work in them. But if there is a force in there that is frictional, there's some kind of friction force that you have to calculate, then you need to use the full form that includes the non-conservative work and the other energies. And on each side of this equation, you're going to get what we call the mechanical energy. The mechanical energy is equal to kinetic energy plus all the kinetic energies plus all the potential energies. That's what it, and then plus the non-conservative work you're dealing with the initial ones. And then the last step is to plug everything in, or actually to get the equation that you need and solve it for the thing that you want to know, and then plug your number in and get an answer, see if it makes sense. So, here are some interesting energies. Daily food intake in joules is 1.2 times 10 to the 7 joules. So 12 million joules of energy we eat on a daily basis. A 1,000 kilogram car at 90 kilometers per hour, 3.1 times 10 to the 5th. Does that surprise you? That a big car, this is not a big car, this is a normal car moving at like, it's like 50, something miles an hour. Does it surprise you that that's actually less energy by, it's 100 times less energy almost. It's like 50 times less energy than this one. Kind of crazy, huh? 1 gram of fat is only 10 times less than the 1,000 kilogram car, right? 1 gram of fat. ATP hydrolysis reaction. That's the reaction that happens in your body to create energy for your body to use. It's about the same as 1 gram of fat. So if you go through 1 ATP hydrolysis reaction, then you burn 1 gram of fat. How much is 1 gram of fat? 1 gram weighs about Now, this is about a 2 gram battery, I would guess. No, maybe about a 1 gram battery. Not very heavy. 1 gram of high carbohydrate is about a half a gram of fat. Tennis ball at 100 kilometers an hour. It's only 22. That's such a tiny amount of energy. 100 kilometers per hour. A mosquito at 0.5 meters per second, almost nothing. An electron on a TV tube beam. Electrons in old TV tubes travel nearly the speed of light, and they have almost no energy to them. Kind of crazy. Huh? But look how much energy it is required to break a DNA strand. Even less energy than that tiny little electron. You know what happens if you break a DNA strand with some energy? Your body tries to fix it. You know what happens if you do that 1,000,000 times in like 15 minutes while you're outside in the sun? Your body tries to fix it 1,000,000 times per minute and makes mistakes. And if it makes just the right mistake, that mistake will actually take over in your body and start making more mistakes. And then it becomes cancer. That's how you get cancer. This is why cancer can happen spontaneously in human beings. Because our bodies are always getting damaged by something. Maybe you get a bruise and you get damaged. Maybe you break a bone and you get damaged. Maybe you get sick and there's damage. Anytime something in your body gets damaged, almost every time, your DNA gets damaged in some way and your body has to come in and fix it. Your body's always fixing DNA. But sometimes it'll make a mistake. And some people are more prevalent to make mistakes. Some people are wired to be more cancer prone. And because their body makes mistakes more often. It's just the way it is. Some people are almost never get cancer. There are some families that have like 0 cancer rate. It just is the way it is. It's not necessarily because of what they eat or their life that they live or whatever else. It's their DNA. It's their DNA. How much energy is in the Big Bang? 10 to the 68. Holy crap, that's a lot of power. When a star explodes, 10 to the 44. That's also a lot of power, but it's not even close to the same amount of power as the Big Bang. Not even close. You say, well, it's only 22 away. Yeah, but that's 22 orders of magnitude. Remember, 3 orders of magnitude is something that's 1,000 times bigger. Just 3 orders of magnitude. This is 22 orders of magnitude. That's like, 1,000. It's like 7 thousands multiplied by each other in a row, plus one more 10. Just crazy. So, here's another thing we need to talk about when we talk about energy. Processes are just not perfect. Conservation of energy is kind of a pie in the sky. It doesn't really happen very often. So what happens when it doesn't happen? Then we start to talk about efficiency. Efficiency is a way of measuring how much energy has been conserved. If you are doing something with some work, but you have to put in more energy to get that work done, then you take the amount of work that was done, divide it by the amount of energy that was required to get that work done, and you'll get the efficiency. The efficiency will come out as a decimal between 0 and 1. It has to be between 0 and 1. If you multiply it by 100, then you'll get a percentage for your efficiency. So here are the efficiencies for different things. Cycling and climbing. So climbing stairs, climbing hills, climbing mountains, and cycling. 20% efficiency, very low efficiency. Swimming on the surface, 2% efficiency. Shoveling dirt, 3% efficiency. Weightlifting, 9%. Right? So which of these activities is the best activity for losing weight? What kind of efficiency do you want if you want to lose weight? Do you want a high efficiency or a low efficiency? High efficiency means that you're doing a lot of work for the amount of energy that you're using. So, for example, if I ride my bike 1 mile with 20% efficiency, then I get 1 mile of work out for every 20 miles of possible energy put in. So, no, sorry, not 1 for every 5. So it's like I put in enough energy to go 5 miles, but I only get to go 1 mile. But if I go swimming on the surface, it has 2% efficiency. In order to go 1 mile on the surface, I actually have to put in 50 miles of energy. So which one of these is using more energy? 1 mile of cycling or 1 mile of swimming? Which one? That one's using a lot more energy, right? So which one's going to make you, if you swim a mile or if you ride a bike a mile, which one's going to make you skinnier? Swimming the mile, right? And believe me, swimming a mile is not easy. I've swum a mile several times in my lifetime. The last time I did it was just a few years ago, but I didn't do it all at once because I was doing it with my boys and they couldn't do it all at once. They were still too young to do it all at once. But the last time I did it all at once, oh man, what was that? I don't even remember when that was. But it's a lot of swimming. If you do it at the pool, if you do it at the pool at Cody Park, the length of the pool, that's 50-meter pool. You have to go 1,600 meters, which is so 1,600 meters would be down and back 20, 40, 60 times down and back. No. $60 laps. 1 lap is once across the pool plus 2, so 62 laps in the Cody pool. It's a 15-meter pool. It's a lot of laps. Without stopping is really hard. In open water, it's even worse because you can't push off the walls. So the last time I did it was in open water. No pushing off walls. No leak. Anyway, electric motors, almost 100% efficient. This is why electric cars are all the rage. They're very, very efficient. They don't have electric heater on here. If they did, you would see the only thing in the world that is 100% efficient. Electric heaters are 100% efficient because all of the energy that goes in just becomes heat, which is what you want it to become. So they're the most efficient heater. But electricity is expensive, so they're not the most cost-efficient heater, even though they're most energy-efficient heater. So that's efficiency for you. Workout over energy. And the problems that they'll give you for this, and they will give you some problems, would be like, there's a power plant that burns, that a power plant has 48% efficiency, so you would put 0.48 here, right? And it does 68 megawatts of, it's a 68, say it's a 50 megawatt power plant or something like that. It has an efficiency of 45%. Well, the amount of watts is something that you would put up here after you converted it. Watts are a measurement of energy per time. So, and then you would calculate the total energy input from that or whatever. We'll learn about that here in a second. Power. So this is what watts measure. Watts measure power. So power is like the velocity that you use energy. It's like the speed at which you use energy. So it's the amount of joules per second. Joules per second. Now this really confuses a lot of people. So for example, the most powerful laser in the world is called the, what is it called? I can't remember. It's called the National Ignition Facility. Yeah. They set a new laser energy record. They fired 2.15 megajoules of energy to its test target chamber. This is a picture of the target chamber. This is not a ladder, in case you're wondering. That's way too big to be a ladder here. This thing is, from here to here, this thing is 3 stories tall. No, actually, this is only the top of the chamber. This is the chamber right here, so this is a ladder. This thing from here to here is just the very top of the chamber. Each one of these things coming down here is our lasers coming into this thing. And this whole thing from here all the way down to the bottom of the chamber is 6 stories tall. So it's about 10 meters. 10 meters, yeah, something like that. It's humongous. They have 192 lasers. Each one of these lasers was the most powerful laser in the world when they built them. Each one of the 192. But then they put them all into one laser, into one chamber, and made the biggest laser in the world. Where is this thing? National. There we go. So here's one of the laser bays. This laser bay is a huge building, huge warehouse type building, and this has half of the lasers in it. Each one of these tubes has one of the lasers in it, and there's 2 of these buildings. And all these lasers shoot down and hit this tiny little target. This target's the size of the head of a pencil, like where the eraser is. And all these 192 lasers come in and hit inside this hole at different angles. And when they come in inside this hole, they obliterate that gold cylinder. They actually vaporize it, turn it into gold vapor. But before they vaporize it, they reflect and hit this tiny little ball at the center of the laser, at the center of the tube, which is a ball that's filled with star material, essentially. It's filled with hydrogen, deuterium, and tritium. And it crushes this ball. All these lasers hit this ball, and they crush it down to something like 1,000 times smaller. And they create a tiny little star inside of this chamber. And then they study it. So this is what this laser does. At that moment, this facility uses more power than the entire United States does. However, that doesn't mean what you think it means, maybe. Even though it's using more power than the entire United States uses in a year or something like this, it's using it in such a short amount of time that it's actually not that much energy. Why? Why is this? Because power equals energy over time. So this is what it looks like. Power is equal to energy over time, the amount of energy used in a certain amount of time. If I use 1 joule in 1 second, it equals 1 watt. The national ignition, well, let's say that the whole country, the whole United States, might use let's say that they use 1 million, they use a lot more than this, but let's just say they use 1 million joules per second. That would equal 1 megawatt. That's 1 million watts, right? But let's say that our National Ignition Facility, which uses, they say right here they're using 2.15 megajoules. So they're using 2.15 megajoules, which was 215,000 joules. That's 2.15 megajoules. And they're doing that, let's say that if they're doing that in 1 second, then that's 2.15 megawatts, right? Which would be more than we use in the United States, but the United States actually uses a lot more than this. But what if they do that in 1/10 of a second, which they actually do it in much smaller than that? They actually do it in like less than 1,000th of a second. But let's say 2.15 joules in 2.15 million joules in 1,000th of a second, which would be 0.001 seconds. If you divide a big number by a very, very small number, or something smaller than 1, you get a much, much bigger number. This is going to end up being 2.15 gigawatts, or 2.15 billion watts. Right? Have you guys ever seen Back to the Future? 1.21 gigawatts. Gotta love that. I think that's actually in this book. Anyway, so so the time really matters a lot here. The reason that the National Ignition Facility can use more power than the United States uses in a day or in a year or whatever it is because they do it in such a short amount of time. It's not a terribly huge amount of energy, but they use it in such a short amount of time that it makes a lot of power. So power is dependent both on energy and time. It's directly dependent on energy and indirectly or inversely dependent on time. Right? So it's kind of like the velocity of energy. How much energy over how much time. Instead of distance over time, it's energy over time. Right? So how much work, how much power does somebody need to climb stairs? We have a 60-kilogram woman going up a 3-meter height flight of stairs in 3.5 seconds. Starting from rest, final speed of 2 meters per second. So how are we going to calculate this? We're going to calculate how much energy there is. She's starting off with no energy. She has 0 potential energy because the bottom is at 0 height, and she has 0 kinetic energy because she's not moving. And then she runs up the stairs, and she ends up with potential energy and kinetic energy because at the top she's running and she's higher up. And so our total mechanical energy is kinetic plus potential. We go ahead and calculate both of those, the final kinetic and the final potential, since the initials are both 0. And then that'll be our total energy used. Once we've got that, we put our total energy divided by the time that it took to do it, and we get energy divided by time, and ends up being 538 watts in the end. So 538 watts to get from the bottom of the stairs to the top of the stairs, from not moving to running at the top of the stairs. So how much energy is that in other units of power? We actually have, we use a unit of power in the United States, especially called horsepower. Horsepower is about equal to 746 watts, or 746 joules per second. Is about how much energy a horse expends, or horse uses. You could think of it as. And this woman's useful output power is slightly less than 1 horsepower, right? People could actually generate more than 1 horsepower with their legs for a short period of time. A horse can do it for a long time. Excuse me. So what happens if she goes up the stairs and just walks up the stairs? Well, then this kinetic energy becomes less because she's not running at the top of the stairs, right? And so the power output would be less. The MGH would be the same, but this is going to be less. And what else is going to be less if she just slowly walks up? The time is actually going to change. It's not going to be less time, it's going to be more time. And you're going to be dividing a number that is smaller by a number that is bigger, and you're going to get smaller power. Okay? In fact, what if she goes up the stairs, but she takes longer to do it, but she's still running when she gets to the top of the stairs? This is the same. This would be, what if she does the same speed? She has the same speed at the top of the stairs, but she just takes longer to do it. Like she just accelerates slower, right? Then all this stays the same on the top, but the time on the top, bottom gets bigger. So you have the same number on the top, but a bigger number on the bottom. That means a smaller number, so less power, right? Here they have some power of different things. So this is how much energy per time. A supernova, the Milky Way galaxy. So one star, when it explodes, uses the same amount of energy per time as the entire Milky Way galaxy does. But remember, the Milky Way galaxy has been doing it for billions of years. A supernova happens pretty quickly and then is over, right? Crab Nebula pulsar of the sun, 4 times 10 to the 26 is cranking out that much power. A football player, 5,000 watts. So a football player could power a clothes dryer. A football player puts out about as much energy as a clothes dryer uses, right? Not bad. It's power, energy, and consumption. So if power equals energy divided by time, you can rearrange that equation so that energy equals power times time, right? And things that we use every day are given power ratings, like a clothes dryer. If you look on the back of your clothes dryer, it will tell you it's a 4,000 watt clothes dryer or 4 kilowatt clothes dryer. If you look on the back of a light or on the top of a light bulb, it'll tell you it's a 60 watt light bulb or an 8 watt light bulb if it's a new LED one or whatever else. An electric clock will have that on the back as well, a pocket calculator. This pocket calculator, as you can, middle 220. 600. I have to do a calculation because they do it in different units on DC devices. This one is like, it's going to be like 200, not even, no, that's not right. It's 200, 5 milliwatts ish. 6 milliwatts. So this is a 6 milliwatts, so it uses 6 thousandths of a watt per second as it's running. Smaller items often use less power. Bigger items often use more power. You can really tell when something uses a lot of power when it's got a lot of heat coming off of it. Because that means when you're using power, generally you're turning that power into some other kind of energy. And oftentimes that's heat energy. The clothes dryer, that's obvious. With a car, a lot of the energy is turned into movement energy. Right? So if energy equals power times time, you can take the power rating of something, like a 0.200 kilowatt computer. So this one uses 200 milliwatts. A computer might use 200 kilowatts, 2.200 kilowatts, which would be 200 watts, and multiply it by the time that it's being used. If it's being used 6 hours per day for 30 days, then you take 6 hours times 30 days and then turn that into seconds and multiply it by actually no, don't even multiply it by seconds because they want it in hours. So what they're doing here is they're using energy. They're multiplying the kilowatts times the hours instead of seconds, and they're using a new unit called kilowatt hours. This unit is just another unit for energy. It's not joules, but it is another unit for energy. Kilowatts times hours is useful because then if you divide, or if you multiply it by the amount that people are charging per kilowatt hour, which is how they charge, then you can figure out how much it costs to run this appliance. So they use the 0.2 kilowatts times the total number of hours, which is 6 times 30, which is 180, of course. Multiply it by 180, you get 36 kilowatt hours, kilowatt times hours. Then you multiply by the 12 cents per kilowatt hour, and you get 12 cents is 0.12, right, dollars. You get $4.32 to run your computer per month for 6 hours a day for 30 days. And there'll definitely be a problem like that in the homework. I'm pretty sure I give you one like that, or maybe two. Yes. So, what we've all been waiting for. How is energy used in humans? Well, this is not perfectly exact because food energy is not the only kind of energy brought into our body. We eat food, but we also breathe in things. So we breathe in oxygen, for example, and oxygen goes into our body and gets broken into different things and used in different things. And in breaking that, it actually creates energy as well. It actually releases some energy. So it's just a small part, but it's also a part of it. But for the most part, food energy comes in the form of these big molecules: sugar molecules, fat molecules, protein molecules, carbohydrate molecules. All these different molecules that our food is made of get broken. When they're broken, that releases energy. When they go through these chemical processes, it releases energy. And some of that energy is used to make other things, like the ATP that we mentioned. How many of you have taken biology and heard about ATP? So ATP is a molecule. It's another type of molecule, but it just happens to be the kind of molecule that our body uses to do things with. So it's kind of like storage for our body, that's energy that our body can use. If our body's going to use it right away, which it often does, the most common thing that it's used for is thermal energy. That's why this arrow in the middle is the biggest. Our body is constantly doing things, even when we're sitting still or sleeping. Our body is constantly doing things to heat itself up, to create heat. So some of those processes are biochemical processes where it's breaking things apart and building new things and releases some heat energy. Sometimes it's just twitching muscles. Sometimes we have muscles in our body, many of them, that just have no purpose but just to move and create heat. That's it. But other things that we do in our body that take a lot of energy and also create a lot of heat is all the neural processes. So all of the electricity that's moving through our body signals between the brain and our different body parts, from one body part to another body part, things like this. All those signals are electrical signals, and all those electrical signals require energy to be moving, and they dissipate energy through heat again. So thermal energy. But then when we actually do something, we move, we talk, whatever we do, that requires some energy here. And all the rest of the energy that's not being used in these two processes goes into fat storage. Now that fat storage has different purposes. Part of it is for energy storage, but part of it is actually for actually making our bodies work properly. So there are different kinds of fat and different uses for that fat. One of the most important kinds of fat is fat in our neural systems. There are certain types of fats that protect our neural cells. There's fat in the brain that protects our brain. There's fat between cells that protect the neurons. There are all kinds of these lipids, they're called. Right? So fats are not just the fat that you have on your stomach. Right? Fat is also has a lot of other purposes in the body and is used very specifically. Fat is also used to store liquid in our body. That's another, when you break up fat, you actually create water, and our body always needs stored liquids in case we get dehydrated. People who have a lot of fat on their body get dehydrated less often than people who don't, because it's a way of storing water. So anyway, let's see here. So here they actually show some of the amount of energy or this power that is consumed by your liver, your brain, skeletal muscle, right? So right here, your brain actually uses just as much energy as your muscles do when you're just sitting still. It's kind of interesting. Of course, when you're moving, your skeletal muscles use a lot more energy. Your kidney, your heart, other things in your body, total of about 85 watts of energy, 85 joules per second of energy being consumed. Oxygen coming in, you can see here it's a little bit more for things that are more, a little bit less for things that are less. Because the oxygen plays a very big role in all these things. Plays a very important role. And then, of course, when you're breathing oxygen in, you are breathing carbon dioxide out. And that carbon and the carbon and the oxygen on the carbon dioxide comes from the things that you eat. So that's how you lose your weight for the most part, is by breathing out. So weight loss from exercising. 12,000 joules, which is a 3,000 calorie diet, consumes 13,000 kilojoules per day, so an extra 1,000 joules. You're going to gain weight. How much bicycling is required to get rid of 1,000 kilojoules? 1,000 kilojoules. So 1,000 kilojoules, 400 watts of energy. So all they've done here is they've solved the power equation for time. Time equals energy over power now. They get 2,500 seconds, 42 minutes of cycling. Now, bear in mind that 1,000 kilojoules is not even 10% over their diet. Their diet is 12,000. 1,000 is not even 10%. So 42 minutes of cycling if you go 10% over your daily allotted intake of food, right? If it's a 2,000 calorie diet, that's 10% of a 2,000 is 200. 200, what is 200 calories? An ice cream, a small ice cream, right? A bowl of cereal is 200 calories. A chocolate-covered granola bar, 200 calories. A small candy bar, like the smallest one you can find on the Walmart checkout, 200 calories. And then you have to do 42 minutes. That's just frustrating. Dang it. You ever ridden a bike for 42 minutes? Like ridden fairly hard for 42 minutes? I've done a lot. I was a very serious cyclist for a very long time. I need to fix my bike and start riding again. But 42 minutes of serious cycling that's a lot of energy. Cyclists are among the skinniest people on the planet because of this. A cyclist that's 6 feet tall will rarely weigh more than 150 pounds. So, and they just have ripping, huge muscles on their legs and their arms, actually. Their arms are fairly strong because climbing requires you pull up on your handlebars while you're pedaling your bike. So energy consumption rate of activities: sleeping 83 watts, sitting 120, standing 125. So people say standing at your desk is gonna make you lose weight faster. Is it gonna do much for you? Not a lot. The reason you stand at your desk is if you have lots of back pain, standing is often better for you than sitting, but not always. Sitting in class, 210. Why? Why more? Why is it almost twice as much? You're thinking. You're writing. You're paying attention. Your neurons are firing. That actually makes a lot of difference. Right? Sitting in class and walking, not that much difference. It's kind of funny. A little bit, but not much. Cycling is pretty high. But if you really want to lose weight, get cold and start shivering. Tennis, fairly high. Swimming the breaststroke. Now this is cycling 13, 18 kilometers per hour. That's like a leisurely cycling. That's like the slowest you can ride without falling over. Cycling at 21 is at 700. A professional racer, 1855. A professional racer averages between 20 and 30 miles an hour on their bike. 1855. Sprinting, like running, sprinting, 2450. Compared to jogging, where's jogging? They don't have jogging. Running cross country, 740. Right? Who's going to get the better workout? Somebody who sprints and rests and sprints and rests and sprints and rests, or somebody who just jogs and jogs and jogs and jogs? Somebody who sprints and rests. They're going to burn more energy by far. It's not even close. So, anyway, and this is all based on fairly low intensity stuff. It goes way up as you get higher in your intensity by a lot. This is an interesting thing. This is an MRI of the brain. Magnetic resonance imaging is a type of imaging where they use. Anybody have an MRI in here? You don't have to say that. So you've been in the chamber and you hear those noises, right? The noise that you hear in there is actually just the coolant. It's cooled with liquid helium, which is at like negative 350, negative 400. It's almost at absolute zero. It's like 5 degrees Celsius above absolute zero, above the coldest you can get in the world, in the universe. So it's like super, super cold liquid helium. And that has to be super, super cold because it's cooling a superconductor, which has a current going, a really high current, going around and around and around that tube. And that creates a really strong magnetic field, which is why you can't have any metal with you, any kind of steel or anything with you inside of it. If you hold one of these lanyards, anybody have like a keychain lanyard? If you hold a keychain lanyard at the door where you go into the room, it will actually stand almost parallel to the ground as it gets attracted into the magnet in the chamber. It's pretty impressive. It's pretty cool. Really strong magnetic field. But what that does is it creates so that the molecules inside of our body they're like little magnets, and you can actually see different things happen with them if you go into this chamber. You can actually watch what happens with them. Different things are made evident essentially as they put you in this magnetic field. And one of the things is that you can actually see when neurons are active, when neurons are these cells with these, that are like little electrical cells, and when they are firing, when they're doing something, when they're active and thinking, or whatever it is you want to call what neurons do, then they show up on the scan. And here you can see the neurons right here are really active. And this is when the person is being asked to recognize something with their eyes. So they're looking at something, they're saying, can you recognize faces or recognize shapes or colors? And different parts, for colors, different parts in the same region will light up. For faces, other things will show up. For shapes, other things will show up. So this is one of the ways that they study the brain. They can also see if the brain is working properly. They can also see if the brain is injured this way. When the brain is injured, it looks different on here. So they can also inject you with things that are magnetic, and so they can inject things into your body so that they can look at different parts of the body in different ways. So if you have cancer, for example, they can inject you with something that will stick to the cancer that will show up on this screen. So, or they can have you breathe something. That's another thing that they can do. So, very, very interesting stuff. The MRI is a fairly new technology, only a few decades, not a couple, but it's a several decades old, maybe 50, 40 years ago they started. It's about the 70s, I want to say 60s and 70s they started inventing it. My dad actually did some research in that when he was young. So world energy use, this is more social science than the last chapter was more biological. This is more social science, economics and things like this. But the energy needs of the world, this is as of 2006, so it's fairly old. Petroleum, huge. Coal, huge. Natural gas, big. Hydroelectricity, a nice slice, hasn't changed much. Nuclear electricity, that's gone up quite a bit in the world. The reason is because it's easily the cleanest renewable resource on the planet, without a doubt. And it's much cheaper than these other ones. All these other little slices, geothermal, wind, solar, biomass, this little tiny slice here are all renewable resources that are extremely expensive. And then of course, hydroelectric, which is dams, those are not terribly expensive, except that you have to build a dam on a river, which changes the landscape of your land, right? It builds a lake somewhere on one side, makes the river small on the other side, it creates all kinds of hoopla and craziness, has to be maintained all the time. This one right here is a renewable resource. So all three of these are renewable, the rest of them are not, right? These ones are all based on things that we essentially dig out of the ground. These ones are not, and this one right here is clean, super clean. The only thing that comes out of it that's not clean are some instruments and equipment and supplies that get radioactive and then have to be stored away. The fuel that gets used in nuclear reactors can be reused. We don't reuse it in the United States. We're the only countries who doesn't. Why? Because our politicians are stupid. That's the only reason. Every other country on the earth reuses their fuel. They essentially put it into a specialized reactor that regenerates it, the fuel, makes it usable again, and they can use it over and over and over again forever. But we don't do that. So these numbers are in billions of kilowatt hours. So this is 3 trillion kilowatt hours from petroleum, so on and so forth. World energy consumption is going up fairly linearly. So you can pretty much be guaranteed that we're going to use more and more energy every year. Here they have some solar arrays in Germany. Contrary to popular belief, most people believe that solar power is just sun shining onto one of these panels and then the panel makes the electricity. Well, that is not the case. That's a very expensive and inefficient way to make solar electricity. But most solar arrays look like this. See if I can find. These are not really what we're looking for right here. So most solar arrays look like this. This is actually just a bunch of mirrors, and they're all pointing towards this center point. Let's actually do a better way to say this is a solar. No, that's not either. So all these panels here, it's not even a real picture, but all the panels that they're showing here, they're kind of the bluish panels. Those are the ones that turn them directly to electricity, and they're super expensive and break down essentially, and then you have to replace them. And making them is actually kind of dirty. They use a lot of chemicals that are just kind of dirty. What most solar is, the way most solar is done, if I can just find an actual solar plant, here we go. This is how it most of the time how it works. These are not solar arrays. This is not powered by solar arrays. This is actually on the ground here. You can't really see them very well, but on the ground here are just a bunch of mirrors, and that's what you're seeing. This white here is just mirrors, and these mirrors are designed to track the sun. They actually move and follow the sun as it goes across the sky, and they all shine up, and you can actually see the light rays right here. They all shine up towards this center tower, and at the center tower, it's got liquid sodium, and the liquid sodium gets evaporated, comes down here and turns turbines, and the turbines turn generators and create electricity. So that is how most solar plants work. Here's a great picture of one. All these mirrors around here that track the sun. This is before the sun has come up. And then when the sun starts to come up, they track it and they shine on the tower, and that's how they work. You'll see these all the time out in the deserts. If you go through Nevada, you'll see them out there. Arizona has them as well. All over the Middle East. And those are really quite efficient and quite effective and quite cheap. It's a really good way to have solar power as long as you have lots of sun and very few cloudy days where you're living. So here is how it goes by country. Let's look at oil. Australia, Brazil, China. China is at 22%. They have very little oil in China. So they have to buy it all from other people. Egypt, which is of course in the Middle East, fairly high because they're in the Middle East. Brazil also has their own oil reserves. Japan, who is rich, so they can buy it from other people. Indonesia is fairly wealthy as well, so they can buy it from other people. U.S. 40%. We're fairly high because we have our own oil reserves. We're much higher now, actually, I think. Natural gas. These companies, these people that have higher numbers are definitely going to be people that have their own natural gas. Russia has a lot of natural gas. Coal. China is huge with coal because they have a lot of coal reserves. The U.S. much lower. India has their own coal reserves, very high. Nuclear power, Australia is at 0. So is New Zealand. And that's because of laws that they've made. And it's actually really hurt their economies. The US is only at 8%. Germany at 11%. Japan at 12%. Most of the European countries are much higher than us, like France and other places. They're much higher in nuclear power. Everybody's pretty low on renewables except New Zealand. New Zealand has a lot of, I'm trying to remember, they have a lot of weird things that they do with the ocean since they're a little island nation. They do a lot of tidal things that go up and down with the tides as the tide's going around. They have a lot of strange things going on like that. Oh, also New Zealand is a volcano. So they actually have geothermal. So they use a lot of geothermal energy where they use the heat energy coming out of volcanic vents. So that's another thing that they have. We have geothermal plants also, mostly in California and Nevada. And since that's where almost all the volcanoes are. California, Nevada, Oregon, Idaho, and I think in Wyoming they have one. That's where all the volcanoes are in our country. So anyway, here you have an interesting table that shows your your gross domestic product per capita, so it's essentially how rich people are, and how much energy they use. So you have the United States, which is very rich and uses a lot of energy. You have Japan, which is even richer than the United States, but uses less energy. Okay? But again, they're an island nation. They have limits to what they can do, how they can expand. So they use less energy because they live in much tighter spaces. Most people live in very, very, very tiny little apartments in Japan. Whereas in the US, we live in much higher, use of everything because we can. Canada, not nearly as rich, but is actually using more energy, right? You hear Canada speak, they'd think that Canada is everything better than the United States, but their carbon footprint is bigger than us, quite a bit bigger than us. Australia, kind of middle of the road with most of Europe here. So here's the world average. Average person in the world is using only 2 kilowatts per person, having about 5,000 per person. So $5,000. So anyway, this is one of the reasons that we are starting to use, lamps in our houses that are more efficient, because more efficiency is essentially going to bring this number down a little bit on this one. But those more efficient things cost more, so it's also going to bring this one down a little bit, right? It's going to bring it down this way, and then costing more will bring it down this way. So we don't want to go down on this scale if we can help it, but we do want to go down on this scale if we can help it. But there's always a little bit of trade-off. You usually have to pay for efficiency. So. You also hear a lot of talk about people saying that China is, vying for the next world superpower with the United States, and there's China right there. That's their domestic product, and that's energy usage. And both of these things have something to do with how well your country is doing, right? China wants to become a next superpower by essentially taking money from the people that should be going to the people and putting it into their military, and putting it into companies owned by the government, so that it makes their government look good. But that doesn't, if you put money into companies that make the government look good, that makes this number go down on the domestic product, and the people can then they can use even less resources. So it makes both these numbers go down, right? So it's not likely, in my opinion, that China is ever going to become a world power. To become a world power, you really do have to have both of these numbers fairly high. Your people have to be happy to be a world power. And to be happy, that means they need to have the things that they want, the things that they need first, and then also some of the things that they want. They don't have to have everything that they want, but they have to have some of them. And that means that this number has to go up, and this number has to go up. It's just a fact of life. And so all of the world powers, all of the great world powers are out in this region here, with the lone wolf Russia being fairly low. They've never been very good at getting their gross domestic product up, mostly because they were ruled by socialists for over 100 years. So anyway, kind of interesting how science leaks over into just about everything. And that finishes up chapter 7 for us. We are now done. So we're done early again. Does anybody have any questions over what you've seen in chapter 7 yet? Or no homework questions or anything like that? I know that you still had some questions from the last homework. You want to talk about, you want to do those right now? You guys don't have to stay if you want to. She's just got some questions about chapter 6. So you guys want to be done? Be done and take off. Good weekend, all that. Hopefully the rain will stop. We'll be able to enjoy the weekend. I love summer where the weekend starts on Wednesday afternoon. Of course, I have to go work at UNL Farm tomorrow on Friday. But that's okay. So which numbers did you have questions on?
Okay, I have 7.
Okay. So I'm going to go ahead and stop my recording first really quick. I have to